Now, let's say this is the plot of a graph given in front of you. You might be thinking what this graph is actually representing. Okay, so let's say on the x-axis, on the x-axis, you have your input size, and on the y-axis, let's say you have time taken. You have time taken. Okay. Now, let's say that this plot is of algorithm 1 and this plot is of algorithm 2. Okay, you have two algorithms. This red plot is of algorithm 1 and this green plot is of algorithm 2. Okay, now if you just carefully see, when you are in this range of input, see, this is the x-axis, right? This is the x-axis, this is the y-axis. So in the x-axis, when you are in this range, that is, your input size is very small. If you see this part where input size is small, see, in this particular region, if you see, then algorithm 1 is working better than algorithm 2. Can I say that? Now you might be thinking why? Because, let me plot it. So for the same input, if you see how much time algorithm 1 is taking and how much time algorithm 2 is taking. So if we plot it like this, let me plot it like this. So if you see, okay, if let's say this is the particular input, then this much time your algorithm 2 is taking, whereas your algorithm 1 is taking this much time. Can you see the difference? Then again, see for few more inputs, right? See here, then see here. Okay, let's see this. So when this is the input, when this is the input, red is the algorithm 1 line, green is the algorithm 2 line. So algorithm 1 is taking less time when compared to algorithm 2. Can I say that? See, for this same value, algorithm 2 is taking somewhere here, whereas algorithm 1 is taking somewhere here. Even if you see here something like this, algorithm 2 is taking something like this, whereas algorithm 1 is taking something like this. So when the input size is very small, definitely algorithm 1 is working way better than algorithm 2. See, but this is the turning point. This is the turning point. This is the turning point. Because if you see this, now for the same input, if now you compare algorithm 1 and algorithm 2, right? So this is for algorithm 1, this is for algorithm 2. Can you see? When the size of the input went beyond the threshold, your green line is what? Algorithm 2. Your algorithm 2 is working faster than algorithm 1. Can you see? So as soon as you are increasing the size of the input, your algorithm 1 is performing worse and algorithm 2 is performing better. So my question is, which algorithm, for doing the same task, which algorithm is better? So technically, technically algorithm 2 is going to perform way better than algorithm 1, because because for small input this time is technically negligible, right? This time is very less. If I just compare it with a magnitude around 10 is per 3, 10 is per 4, then, and even beyond that, this time is very less. And even the difference is less. See, here, this was algorithm 2, sorry, this was algorithm 1, this was 1, and this was 2. So the time difference is not much. Although, yes, algorithm 2 is performing bad, but it's not performing way bad. But if you compare the difference here, this difference is huge in terms of magnitude, right? This difference is huge in terms of magnitude. So what we know is our computers can perform 10 raised to the power 8 instructions in 1 second. So for small values, the number of instructions involved will be approximately very less. So we technically don't care about very small input. That for a very small input, let's say if an algorithm is working very good, that should not be our judgment criteria. Our judgment criteria should be when the algorithm becomes, or when the input becomes very huge, how the algorithm is performing. Because if you see, then this algorithm, this curve of algorithm 1 is, after very long period of time, it's going to go parallel to y-axis, right? Right. My point being that always we care about how the algorithms are performing for large input size, for large input size. And based on this theory, we are going to devise a new way of checking an algorithm. And if I ask you a question that why algorithm 1 after some period of time started performing worse than algorithm 2, something that started very well, why it was not able to continue in the same fashion? Because of this thing. So there is a term called as rate of growth. There is a term called as rate of growth. What is rate of growth? Let me talk about that. So rate at which rate at which running time increases as a function of input is called rate of growth, right? So if you see, then the growth, that means the increase with every change, let's say with every small change in the input, do you see how much change? Let me draw it like this. Let's say with a small change in input like this, if you carefully see, the change in time is extremely huge. See, this is the change in time, right? Whereas if you compare it with algorithm 2, the change is very less. So that's what growth is. Growth means at what rate you are changing the running time if the function, or let's say if the input size increases or decreases. That is how fast your rate of change of time is increasing, right? If you see, this curve is increasing way faster, or the values on the y-axis is going to increase way faster when compared to this curve, right? You might have, if you are coming from a science background, you might have heard about this term rate. For example, rate of change of velocity, rate of change of displacement. These kind of terms you might have heard, but if in case you are not coming from a science background and or a physics background, and you have not heard about this term rate, then in simple term, rate of growth means the rate at which change the running time increases or changes with change in input. And when I say rate, then you mean that with respect to the input, how much the time is changing. If your growth rate is more, then your time taken will become huge, right? And if your growth is less, then going to take less time. Just think about it. If there are two companies, one company is growing at a faster rate, that means their I would say overall profit is faster. For example, in the first quarter, the company one, there are two companies, company one and company two. Company one made a profit of 100 rupees, company two made a profit of 20 rupees. In the second quarter, company one made a profit of 105 rupees, but company two made a profit of 80 rupees. In quarter 3, company 1 made a profit of 110 rupees, company 2 made a profit of 140 rupees. Do you see which is a better company to, let's say, actually bet on? Company 2 looks better because their profits are increasing by a significant margin. Although when you compare till second quarter, it's less than company 1, but they were increasing at a higher rate. Their profits were increasing at a higher rate. That's why actually their profit is going to explode after some time, because their overall growth of the company is increasing exponentially. So at some point of time, their profits are going to surpass by a very huge margin to C1. Similar thing is here. If your running time is increasing extremely faster with a very small change in the input, see this. If runtime changes extremely high with a small change in input size or input, then growth is high, right? Then growth is high. So how do you mention change? So you mention it like delta, right? So change in time with respect to change in input, right? If this change in time is very much with respect to very less change in input, then the overall rate is going to be very high. The overall rate is going to be very high. That's what I want to say. So there are two observations that we can make from all of this discussion. First thing, whenever we are comparing algorithms, we don't care about small input sizes. We always care about big input size, that how my algorithm is going to perform on bigger inputs. First thing. Second thing, we are going to judge algorithms based on their rate of growth, that how fast the time is going to change with a very small change in the input. Based on these two terms, we introduce a new way of analyzing algorithms called as asymptotic analysis. And this is the industry, I would say, accepted, or let's say any algorithmic analysis research paper or anything you will read, this is the accepted way of analyzing algorithm. It is independent of the hardware, it is independent of the CPU conditions that you are going to run your algorithm on, and instead it is going to judge the algorithm based on the rate of growth and the I would say how the algorithm is performing for very high input. That's what we are going to actually do in asymptotic analysis. So this word asymptotic analysis is actually coming from the word asymptote. It actually comes from the word asymptote. Although it's not very much related to the overall asymptotic analysis theory. But what is an asymptote? It is a straight line. It is a straight line that constantly approaches a given curve, right? But doesn't meet doesn't meet at any infinite distance, right? So let's say if you have a curve like this, sorry, if let's say you have a curve like this, sorry, right? Let's say you have a curve like this, then maybe this can be some asymptote that's never going to like meet the curve at some value infinity. Let me just shift it somewhere here, right? Something like this is an asymptote. Although it doesn't make a lot of like difference if you don't even know about asymptotes. Why we do this? Because asymptotes, the equations of asymptotes are generally handled for very high values, for very big values. And in our analysis also, we are going to only focus on very big input sizes. We are going to only concern about very big input sizes. So asymptotes as a curve are mainly, I would say, related for very high values. That's why we call it as asymptote. Although it's there is nowhere specifically mentioned that why this is called as asymptotic analysis, but this is some of the reasons that you will find very easily on the internet. So now we have to understand what is asymptotic analysis. So actually asymptotic analysis is based on majorly two terms. First is rate of growth of algorithm, that is running time with respect to input size, and behavior of the rate at very high value, at very large input value. These are going to be the two major criterias based on which we are going to do everything around asymptotic analysis. So now we know rate of growth matters a lot for the analysis of algorithms. So I'm going to show you the curves of some common rate of growth functions that will be used in your day-to-day analysis of an algorithm, right? That is when you will analyze, like how we will analyze and how we will reach these curves, we are going to talk about that. But for the timing, like at least I'll let you know that if you see an equation like this, then it will be having a higher rate of growth. So something like y is equals to x square is there, right? Or maybe I can start plotting it again, right? So let's start. So you can have something like y is equals to n factorial. See, n factorial is almost parallel to y axis only, right? Then there is y is equals to 2 raised to the power n. Okay, this black line, is y is equals to 2 raised to the power n. Then let's say y is equals to n cube. Okay, this red line is n cube. I'll show all of them, don't worry. Then y is equals to, let's say, n square. This blue line is n square. Then y is equals to n log n is this green line, and y is equals to, this should be n root n. Can we do root? Um, okay, this is y is equals to root n, this green line. Okay, this is y is equals to n log n, and it should be n into root n. Then y is equals to n, y is equals to root n, y is equals to log n, and then let's say there will be y is equals to log of log n, but we can even avoid it, it's very similar to the others. And let's say y is equals to some constant, let's say y is equals to some constant c, right? You can put the value of c as anything, let's say 3. Okay, so these are different curves. I know the overall diagram looks humongous, right? So let me just show you from the positive part only. Okay, so n factorial, n factorial is technically, n factorial, let me just put it here, is the worst performing rate of growth. If the rate of the growth of the algorithm is n factorial, that's the worst. A bit better than n factorial is 2 raised to power n, but still it is very bad. If I just disable the rest of the curves, if I just disable the rest of the curves, you see, for some period of time, n factorial is better than 2 raised to the power n, but after a threshold, n factorial is a bit more bad than 2 raised to power n. But if you see a very big picture, then technically both of them at a very long, like after some time, are going to become parallel to y-axis. So they are almost equally bad. Like it's not like one is like much worse and one is better. They are equally bad, but still n factorial performs a bit worse. Then you have y is equals to n cube. Just think about it. N cube is better than 2 raised power n and n factorial, but the rate of growth on n cube is still a bit worse. You can see after some time, n cube is between n factorial and 2 raised power n. But if you just scroll a bit more, if you go for a bit higher value of n, more higher value of n, then after some time, see, now the black and the red line are overlapping each other, and then red line is going to come towards the right. That means the rate of growth of n cube for higher values of n, right, is a bit better than 2 raised to the power n. It's a bit better. So if you just zoom it out a lot, and if you see, it will look like that these are similar, but if you just actually see the graph, then after a big value of n, or like after some change, that it becomes better than 2 raised to the power n, right? So let me repeat all the three curves again. Okay. So let me go to the x-axis. So see, just see the positive side. Just see the positive side. This is the y-axis. Okay. So if you just see n factorial, this is the curve for n factorial. You can see with a very less change in the value of n, the curve is going almost parallel to y-axis, right? And why? Because the rate of growth of n factorial is very high. Rate of growth of n factorial is very high. Like if you have a function or if you have an algorithm that changes the runtime with respect to the input size change at a rate of growth of n factorial, then it's very high. It's very bad. A bit better than n factorial is 2 raised per n. You can see 2 raised per n is a bit better because you can see it's on the right side of this purple curve, right? So for some values, you will feel that it performs a bit better than n factorial. It's on the right side. So the closer you come to the x-axis or the n-axis, the better is the algorithm. So the black line, you see, black line is a bit closer to the n-axis, right? Okay. Then you have n cube. N cube initially will feel like that it is worse than n factorial and 2 raised per n. See, n cube is to the left of both of them. But after some time, let's say for some higher values of n, n cube will become better than n factorial and 2 raised per n. And that's what our agenda is also. For higher values, we only care. So if I just zoom out so that I can show you some higher values, if I zoom out and go for something a bit up, that is not much change. Then now here you can see the red line is to the right of the black and the purple line. So that signifies that after some change in the value of n, the value of n cube, it becomes better than 2 raised to the power n and n factorial. Okay, cool. Just a moment. Okay, let's come back. Now you have like this curves that I'm writing. No, these are like some common rate of growth that you will see in a lot of algorithmic problems. Okay, now you will see something like n square. Now you see this blue line, this sky blue line is n square. It is better than all of the other three, but still after some time, the rate of growth is very high. Then you have something like n root n. N root n is this green line. See, if you go from n square to n root n, see the curve is significantly better. And just think about it. If let's say there is a curve y is equals to n square, if the value of n is 10, then this will give you 100. But if the value of n becomes 10 raised to the power 5, this curve will give you what? 10 raised to the power 10. Whereas if you have something like y is equals to n into root n, and let's say you have a value n as 100, this is going to give you what? 100 into 10, that is 1000. But if the value of n becomes 10 raised to the power 6, let's say, then it will be 10 raised to the power 6 into root of 10 raised to the power 6, that is 10 raised to the power 9. So see, for an even higher value of n root n gives you better value when compared to n square. So n root n is a better function in terms of rate of growth. Then after n root n, even better one is n log n. You can see n log n. This line is even better, even closer to the x-axis. Then y is equals to n. It initially performs a bit bad with respect to n log n, but later it becomes better than n log n. Just think about it, right? If let's say you have a curve of y is equals to n log n, and this is y is equals to n. If the value of n becomes 10 raised to the power, let's say 3, so this will be 10 raised to the power 3 into 10, that is 10 raised to the power 4, whereas this is going to be just 10 raised to the power 3, right? If the value of n will become 10 raised to the power 6, this will become 10 raised to the power 6 into 20, that is 2 into 10 raised to the power 7, whereas this will be 10 raised to the power 6, right? So approximately, these are approximate numbers, okay? These are approximate numbers. Then we have something like root n. See, root n is significantly better than y is equals to n. Then you have something like log n. Log n is even better than root n. And then you have some constants. Now, when there is a constant, constant never grows, right? If you have a curve like this, if you have a curve like this is, let's say y is equals to, let's say 5. Now, with respect to change in input, this curve is not changing, right? The value still remains same. So that's a constant curve. That means with change in input, the time taken is not going to change. The time taken is going to be constant. So the time taken becomes independent of the change in input. That's why you see y is equals to 3 is above log n. But after very large value of n, log n will surpass y is equals to 3. But y is equals to 3 is going to remain same. So technically its time doesn't change. So these are the different important curves that I have listed. So I'll just take a screenshot quickly, so that you can even understand how these curves look like. And actually, these curves are the most common, I would say, functions that you will see in terms of your algorithmic analysis, where you will actually be using this data, that which curve works better and which curve doesn't work better. Right, we'll see some examples. But my point of this discussion was to make you understand how exactly rate of growth actually works, right? So if I write here, this is the worst, this is the best, and we are coming from worst to best. Okay, worst to best. So whenever we will talk about rate of growth, we talked about this term rate of growth, that how your time is changing with respect to input size. If we have two algorithms, in the first algorithm the rate of growth is n square, in the second algorithm the rate of growth is square root of n, then definitely this algorithm is better. This algorithm is not that better because the rate of growth is high. You can say high rate of growth, right? Here you can say slow rate of growth, slow rate of growth, right? So if a function is having, or if an algorithm is having high rate of growth, then we don't desire that algorithm. We always desire an algorithm with a slow rate of growth. Now the second point that I wanted to highlight was that we only care about very big values. Now just think about it. Let's say if there is an algorithm, the rate of growth of the algorithm looks something like this: 3x square plus 8, something like this, right? And let's say there is another algorithm which is having 10x to the power 5 plus 3x to the power 3 plus 2x plus 10. Okay, this is algorithm 1. This is, or let's do it like, this is algorithm 2. This is algorithm 1. Okay, which algorithm is better? Now you might think that, okay sir, now the situation is very complex. You just told us about simple functions, simple equations. This is quite complex, right? That's where our second notion comes into the picture, that because we are not doing math here, we want to analyze complexity of an algorithm, and we know that complexity of the algorithm only matters for very high value of the input. So let's consider something like x to be of the magnitude of 10 raised to the power 6. If you consider something x like of the magnitude 10 raised to the power 6, this will become what? 3 into 10 raised to the power 6 square plus 8. Now just think about it. 10 raised to the power 6 square plus 8, this is negligible, right? This is going to be 10 raised to the power 12. 3 into 10 raised to the power 12 plus 8. This is negligible. Just think about it. If your computer has to execute 10 raised to the power 12 instructions, and it can execute that efficiently, I don't think executing 8 more instructions is of any concern to the computer, right? Apart from that, 3 into 10 raised to the power 12 is also 10 raised to the power 12. 10 raised to the power 12 is a so big number that even if you multiply some constant with it, you can even avoid it. This is also avoidable, right? Same thing here. Now just think about it. If x y is equals to 10 raised to the power 6 goes here, this will be 10 into 10 raised to the power 6 whole raised to the power 5 plus 3 into 10 raised to the power 6 whole raised to the power 3 plus 2 into 10 raised to the power 6 plus 10. Now just think about it. 10 raised to the power 6 whole raised to the power 5. All of this is negligible. All of this is negligible. For this high value of the input, all of this is negligible. Even this is negligible. Right? That if the values of the magnitude 10 raised to the power 6 whole raised to the power 5, right? It doesn't even matter whether it is getting multiplied by one more 10 or not. It's extremely huge already. And rest of the values also doesn't matter because they are extremely small. They are extremely small. That is why in asymptotic notation, what we do is we avoid all constants and lower degree term. Lower degree terms. We only concern ourselves with the highest degree term. With the highest degree term. That means if you get two algorithms, first algorithm works like 3x square plus 8 instructions. Next algorithm works like this. So technically you don't have to compare these complex equation. All you have to compare is algorithm 1 works approximately like x square and algorithm 2 works approximately like x raised to the power 5. You can just compare your highest degree term in terms of approximation, because in approximation you can just avoid all the lower degree term. So these are lower degree terms. See, these are lower degree terms. Lower degree means the power of these terms in terms of x is very less. Here x raised per 5, but here only 3, here only 1, here was 0. So lower power of x are going to be avoided, and this is a constant. Even constants can be avoided. This is also a lower power term or a lower degree term, right? So all you can do is you can avoid lower degree term and constants, because just think about it. If for some value of x, your algorithm 1 looks like better, if it is executing 3x square plus 8 or it's executing x square, almost same, right? If the value of x is so high like 10 raised per 4 or 10 raised per 5 or 10 raised per 6, 3 into 10 raised per 6 square is not going to matter a lot. It's equivalent to 10 raised per 6 whole square. That's why we said, and that's what the application is, that we will be measuring rate of growth and in terms of instructions, that how many instructions you are executing, and we will concern ourselves with very high value of the input only. We don't care about the lower input values, because in the lower input values maybe some function works worse than the others, but that's not our concern. See, even in these curves there are a lot of functions that are not initially working well, but after some time they surpass the worst function, right? So my point being that you don't care about smaller degree terms, you always care about just the higher degree terms or higher values that can actually make the number of instructions to be executed go much higher. That's what our concern is. So based on these two facts about the rate of growth as well as like avoiding the lower degree term and constants, we are going to start reading and start learning about how to analyze an algorithm.